The universe is the entirety of everything that exists, encompassing space, time, energy, matter, galaxies, stars, planets, and all other forms of cosmic structures. It is the vast expanse in which all known and unknown entities interact and exist. As for the origin of the universe, one widely accepted scientific model is the Big Bang theory. The Big Bang theory proposes that the universe originated from an extremely hot and dense state. Around 13.8 billion years ago, the universe is thought to have been in a state of singularity, a point of infinite density and temperature. The Big Bang event occurred when the singularity began to rapidly expand, initiating the expansion of space and the decrease in temperature. As the universe expanded and cooled, energy and matter formed, leading to the creation of galaxies, stars, planets, and everything we observe today. While the Big Bang theory is widely accepted, it doesn't address all aspects of the universe's origin and evolution. Ongoing research and exploration continue to refine our understanding of the universe's birth and development. New models and theories may emerge as scientists seek a comprehensive explanation for the complexities observed in the cosmos. We learn about the universe and its structure through various means of observation and scientific research. Here are some primary methods by which we understand the universe. Spectroscopic observations. Instruments for spectroscopic observation allow us to analyze the light emitted by celestial objects. Spectral data provides information about the chemical composition, temperature, and motion of objects. Telescopes and observatories. Ground-based telescopes and observatories worldwide provide high-quality images of celestial bodies such as stars, planets, and nebulae. Space telescopes. Instruments like the Hubble Space Telescope, placed in space to avoid Earth's atmospheric interference, deliver sharp images of a broad spectrum of the universe. X-rays and gamma rays. Observing X-ray and gamma-ray radiation helps us see cosmic events that are not visible with the naked eye, such as black holes, supernovae, and high-energy phenomena. Radio telescopes and radio observatories. Observing radio waves aids in studying cosmic phenomena like star clusters and galaxies, utilizing radio waves instead of visible light. Computer simulations and mathematical models. Using computer simulations and mathematical models to simulate and understand the structure and evolution of the universe. Space exploration. Space exploration missions like Apollo, Voyager, and modern missions like Curiosity on Mars provide direct information from planets and other celestial bodies in our solar system. All these methods, combined, provide us with a comprehensive and multidimensional view of the universe and its intricate structure. A stellar explosion, or supernova, is a powerful and significant event in the universe, generating immense energy and influencing the surrounding environment. There are two main types of stellar explosions, nova and supernova. Nova. Novae occur when a binary star system, consisting of a white dwarf and another star, transfers material onto the white dwarf. When this material reaches a critical amount on the white dwarf's surface, it triggers an extremely bright outburst. Although novae can be quite luminous, they typically last only for a few days or weeks. Supernova. Supernovae are more powerful explosions, releasing much more energy than novae. There are two main types of supernovae. Type Ia supernova occurs when a white dwarf in a binary system accumulates too much material from its companion star, leading to overloading and explosion. Type II supernova occurs when a massive star reaches the end of its life cycle. As the nuclear fuel in the star's core depletes, the balance between internal pressure and external gravitational forces causes the star to explode. Consequences of a supernova. After a supernova event, energy and matter from the exploding star are ejected into space. These explosions enrich the universe with the necessary chemical elements for the formation of new stars and planets. Heavier elements beyond iron, such as gold and uranium, are often synthesized during supernova events. These events not only contribute to the chemical enrichment of the universe but also have a profound impact on the structure and development of stellar systems and galaxies. The question of extraterrestrial life is one of the greatest mysteries in science. Currently, there is no concrete evidence of life beyond Earth, but there is also no definitive evidence ruling out the existence of extraterrestrial life. Here are some avenues that science explores in the quest to understand the possibility of extraterrestrial life. Life within the solar system. Space exploration missions, such as Mars rovers and planned missions to the moons of planets within our solar system, aim to search for signs of life. Exoplanets. Observing exoplanets within the habitable zone of other star systems to determine the potential for water and conditions conducive to life. Search for scientific signatures. Listening and observing signals from space to search for messages or signals from intelligent extraterrestrial civilizations. Investigating life in harsh environments. Studying life in extreme environments on Earth, such as in high-temperature, saline, or oil-rich environments, to understand the potential for life in environments beyond Earth. While there is currently no direct evidence of extraterrestrial life, ongoing research and exploration efforts continue. These endeavors help us gain a deeper understanding of the diversity of the universe and may eventually provide answers to one of humanity's most profound questions. A black hole is a physical phenomenon where gravity is so strong that it causes space and time to collapse around it. For many, a black hole is often described as an area in space from which nothing, not even light, can escape. Here's how black holes form and operate. Formation of black holes. Black holes often form when a massive star concludes its life cycle and explodes into a supernova. During this process, the extremely strong gravitational forces compress the matter into a very small space, creating an intense gravitational pull. Event horizon. The event horizon is a theoretical boundary that marks the point where space and time are terminated by the gravity of the black hole. If an object crosses the event horizon, it cannot escape the gravitational pull of the black hole. Space-time singularities. At the center of a black hole, where matter has been compressed, there may be a space-time singularity, a region with extremely high density and infinite gravitational forces. Light absorption zone. Black holes have the ability to absorb light, making them appear invisible in direct observational spectra. This gives the impression that nothing can escape from a black hole. Time and space warping effects. In the vicinity of a black hole, time passes more slowly compared to areas farther away due to the influence of strong gravity. Black holes are not only an intriguing aspect of physics but also play a crucial role in the study and understanding of the universe's structure. Exploring the universe poses numerous challenges, ranging from technological and engineering hurdles to scientific complexities and ethical considerations. Here are some key challenges in the exploration of space. Technological and engineering challenges. Vast distances, stars and planets are extremely far away, demanding superior technology for exploration and communication. Time and energy. Space exploration missions are lengthy and require substantial energy resources. Maintenance and repairs. Maintaining and repairing equipment in the harsh conditions of space is a significant challenge. Human protection. Radiation and health factors. Space radiation and the effects of space conditions without atmospheric protection necessitate safety measures for space explorers. Microgravity impact. Prolonged exposure to microgravity can impact the health of individuals spending extended periods in space. Costs and resources. High expenses. Developing and deploying space exploration missions involves substantial investment from nations or international organizations. Limited resources. Resources such as fuel and materials may be limited for long-duration and long-distance space missions. Scientific issues. Understanding the universe. Many mysteries of the universe remain, and complex missions are necessary to answer fundamental questions. Extraterrestrial life. The question of whether extraterrestrial life exists is a significant scientific challenge. Space environmental protection. Space debris. The increasing amount of space debris poses collision risks with exploration objects and satellites. Legal and ethical considerations. Sovereignty and space law. Issues of sovereignty and space law become complex with the growing involvement of nations and organizations in space exploration. These challenges call for global collaboration and technological innovation to efficiently and sustainably understand and explore the universe. The universe is still filled with many mysteries that we have yet to decipher. Here are some of the most significant mysteries and scientific questions that continue to baffle researchers. Dark matter mystery. Dark matter constitutes about 27% of the universe, but its true nature remains unknown. It is a form of non-luminous matter that does not interact with light but exerts gravitational effects. Dark energy enigma. Dark energy comprises approximately 68% of the universe and is the primary driver behind the accelerated expansion of the universe. The characteristics of dark energy remain a major mystery. Higgs boson puzzle. Despite the discovery of the Higgs boson at CERN in 2012, many details about why and how it interacts with other particles remain mysterious. Origin and expansion of the universe. Our understanding of the origin of the universe and why it is expanding at an accelerating rate is still incomplete. Extraterrestrial life. The question of extraterrestrial life is still a mystery. Whether there is life beyond Earth and, if so, how we might find it remains an open question. Black hole information paradox. The black hole information paradox raises questions about information loss when matter falls into a black hole and whether the principle of information conservation is preserved. Cosmic microwave background anisotropy. Irregularities in the cosmic microwave background radiation present a mystery, challenging our models of the formation and evolution of the universe. These mysteries, along with many other aspects of the Sun is a star located at the center of the solar system and serves as the primary source of light and energy for the system. Below is a description of the Sun and how it operates. 1. Basic characteristics. Structure. The Sun is predominantly composed of hydrogen, about 74% by mass, and helium, about 24%. Heavier elements make up a small portion. Temperature and pressure. The average temperature of the Sun is around 15 million degrees Celsius, 27 million degrees Fahrenheit, at the outermost layer called the corona. Pressure and temperature increase from the core outward to the surface. 2. Nuclear fusion process. Fusion. In the Sun's core, hydrogen undergoes fusion, transforming into helium through the fusion process. In the core, due to extremely high pressure and temperature, hydrogen particles are compressed, forming helium and releasing a significant amount of energy according to the equation E equals mc²2, Einstein's law. Solar energy. Energy from the fusion process converts into light and heat, generating gravitational force and pressure from this hot gas mixture, creating a balance in the solar furnace. 3. Heat and light transmission. Solar light. Energy from the fusion process radiates outward, forming light and heat. This is the primary source of light for the Sun. Heat transmission. Light and heat are transmitted out of the Sun and reach the Earth, providing energy for life and contributing to climate phenomena on the planet. The Sun sustains life and the activities of the solar system by supplying energy and light to the planets and other objects within the solar system. Planets orbit the Sun due to the force of gravity, an attractive force acting between Earth and other objects in the solar system. This is a phenomenon specifically described by Newton's law of gravity. Gravity. Gravity is the force of attraction between two objects with mass. In other words, every object with mass exerts a gravitational force on every other mass. Newton's law of gravity. Newton's law of gravity describes the gravitational force between two objects. According to this law, each object exerts a gravitational force on the other object, with the force magnitude proportional to the product of their masses and inversely proportional to the square of the distance between them. Circular motion and Kepler. When an object moves in a circular trajectory around another object, such as a planet orbiting the Sun, the gravitational force and the momentum of the motion create a circular or elliptical orbit. Kepler's 3 laws describe the motion of planets around the Sun. These laws explain the orbiting, structure, and time ratios of planetary motion. Planets orbit the Sun due to the balance between gravitational force and the momentum of motion, creating orbits that maintain the stability of the solar system. Planets do not move in a straight line, instead, they orbit the Sun in specific trajectories. The Moon orbits the Earth due to the gravitational interaction between these two bodies. This is an example of a smaller object, the Moon, orbiting around a larger one, the Earth, due to gravitational forces. Here is a detailed explanation. Gravity. Each object with mass creates a gravitational force. For the Moon, the gravitational force is primarily generated by the Earth. Gravity and momentum. The Moon was initially formed from materials in Earth's atmosphere, hypothesized by the giant impact hypothesis. Due to the mass of the Moon and the distance between the Earth and the Moon, the gravitational force between them generates a momentum. The momentum creates a rotational motion around the Earth, forming the Moon's orbit. Circular or elliptical orbit. The Moon moves along an elliptical orbit around the Earth. This is the result of a balance between gravitational force and momentum. Tidal interaction. Tidal interaction between the Earth and the Moon also plays a role in slowing down the Moon's rotation. It increases the gravitational force between them, leading to a synchronous rotation where the same side of the Moon always faces the Earth. In summary, the Moon orbits the Earth primarily due to the gravitational interaction, combined with factors such as tidal interaction and momentum, creating a stable dynamic system between these two bodies. A nebula is a vast, cloud-like structure in space, often taking the form of large, colorful clouds. They are typically observed through the light emitted by nearby stars or other light sources. Nebulae are formed through the process of star formation and can later become sites for the formation of planetary systems and other star systems. Here's how nebulae are created. Formation of nebulae. Nebulae often form from elements and chemical compounds expelled from stars when they reach the end of their life cycle without having enough energy to maintain the balance between gravitational forces and thermal pressure in the core. Radiation from nearby stars can stimulate the molecules and dust particles in the surrounding space, creating the bright and colorful appearance of nebulae. Types of nebulae. Emission nebulae. Emission nebulae are primarily created by young, hot, and bright stars. They often contain elements such as hydrogen, helium, oxygen, and other light elements. Dark nebulae. Dark nebulae are often seen when stars age and evolve into red giants or supernovae. They contain more dust and larger particles, giving a sense of darkness. Star formation and stellar systems. When a new star forms from a cloud of gas and dust, part of the surrounding material is blown away, creating nebulae around the newly formed star. Throughout the evolutionary process of a star system, nebulae can also house planets, stars, and other stellar systems. In summary, nebulae are fascinating space structures created from materials expelled by stars and often serve as the birthplaces and developmental grounds for the universe. Star clusters in the universe exhibit a tremendous diversity in both characteristics and structures. Star clusters can vary in terms of size, mass, temperature, stellar class, as well as in the energy processes and internal compositions. Here's a description of this diversity. By size and mass. Dwarf stars. Dwarf stars are smaller in size and mass compared to other stars. They can be newly formed stars or stars that have exhausted their fuel and contracted. Small and massive stars. Star clusters can contain various types of stars with diverse sizes and masses, ranging from stars smaller than the Sun to extremely massive stars known as supergiants. By temperature and color. Hot stars. Hot stars often appear blue, white, or cyan. These are typically young and bright stars. Cool stars. Cool stars have a red color and are often older stars, such as red dwarfs and red giants. By stellar evolution and age. Young and old stars. Star clusters may contain stars at different stages of their evolution. Young stars are often found in open clusters and star-forming regions, while older stars may dominate in more mature star clusters. By structure and shape. Binary star systems. Star clusters may contain binary star systems, where two stars orbit a common center. Open clusters and globular clusters. Open clusters often harbor young stars, while globular clusters tend to have older stars. By interaction and gravitational forces. Binary systems and multiple systems. Stars in clusters can interact and feel gravitational forces from each other. In some cases, stars may undergo interactions, collisions, or even mutual gravitational attractions. By dynamics and motion. Star streams. Over time, star clusters may exhibit dynamic motion, leading to the formation of star streams as stars move within the cluster. Star clusters demonstrate a rich and varied tapestry in the universe, providing valuable insights into the formation and development of stellar systems and the cosmos. We have day and night due to the orbit of Earth around the Sun, coupled with Earth's rotation on its axis. This natural phenomenon originates from the structure and motion of our planet. Here's how we have day and night. Orbit around the Sun. Earth moves around the Sun in an elliptical orbit. The Sun is located at one of the two focal points of this ellipse, referred to as one of the 2 points of day and night. Rotation on its axis. Earth rotates on its own axis, known as the rotation axis. The time it takes for Earth to complete one full rotation on its axis is called a day. Impact of sunlight. As Earth rotates on its axis, a portion of the planet receives light from the Sun, creating daytime in that region. Simultaneously, another part of Earth is in the shadow, not receiving sunlight, resulting in nighttime. Seasonal changes. Throughout the course of a year, Earth not only rotates on its own axis but also orbits around the Sun. This introduces variations in the angle of sunlight on Earth's surface, causing changes in the length of day and night. In summer, a specific region may receive sunlight for a longer duration, resulting in longer days, while another region may experience shorter days. In summary, day and night occur due to the combination of Earth's orbit around the Sun and its rotation on its axis, coupled with changes in the angle of sunlight throughout the year. We have day and night due to the orbit of Earth around the Sun, coupled with Earth's rotation on its axis. This natural phenomenon originates from the structure and motion of our planet. Here's how we have day and night. Orbit around the Sun. Earth moves around the Sun in an elliptical orbit. The Sun is located at one of the two focal points of this ellipse, referred to as one of the 2 points of day and night. Rotation on its axis. Earth rotates on its own axis, known as the rotation axis. The time it takes for Earth to complete one full rotation on its axis is called a day. Impact of sunlight. As Earth rotates on its axis, a portion of the planet receives light from the Sun, creating daytime in that region. Simultaneously, another part of Earth is in the shadow, not receiving sunlight, resulting in nighttime. Seasonal changes. Throughout the course of a year, Earth not only rotates on its own axis but also orbits around the Sun. This introduces variations in the angle of sunlight on Earth's surface, causing changes in the length of day and night. In summer, a specific region may receive sunlight for a longer duration, resulting in longer days, while another region may experience shorter days. In summary, day and night occur due to the combination of Earth's orbit around the Sun and its rotation on its axis, coupled with changes in the angle of sunlight throughout the year. A black hole is a region in space where gravitational forces are extremely strong, to the extent that not even light can escape from it. The gravitational pull is so intense that it forms a boundary known as the event horizon, beyond which nothing, including light, can escape. Here is how black holes are formed and how they operate. Formation of black holes. Black holes typically form when a massive star exhausts its fuel and undergoes a gravitational collapse, creating a highly concentrated mass in space. The energy released during this collapse can generate an extremely strong gravitational pull, creating a black hole. Black holes can also form through the collapse of other celestial bodies or through the merging of smaller black holes. Acceptance of gravitational force. Black holes exert an incredibly strong gravitational force. For a non-rotating black hole, the event horizon is the boundary beyond which no object, including light, can escape the gravitational pull. Anything that crosses the event horizon is drawn into the black hole and cannot return. Rotation around an axis. Some black holes have the ability to rotate around an axis, creating a swirling effect and unique physical phenomena like spinning around a black hole. Hawking radiation. Stephen Hawking's theory predicts that black holes can emit a small amount of thermal radiation through a phenomenon known as Hawking radiation. This implies that over time, black holes may lose mass and energy through this process. Impact on surrounding space. Black holes can also warp the space around them, causing space-time to curve and even affecting time in an effect known as space-time curvature. Black holes are one of the most intriguing phenomena in physics and astronomy, serving as a deep area of study in both fields. If an object falls into a black hole and crosses the event horizon, according to modern theories of black holes, it cannot escape for the following reasons. Incredibly strong gravitational force. Black holes possess an extremely strong gravitational force to the point where space around them is profoundly disturbed. This results in a gravitational pull so strong that any object crossing the event horizon is drawn into the black hole. Event horizon. The event horizon is a virtual boundary around a black hole where the gravitational force becomes strong enough that even light cannot escape. If an object passes this boundary, it has fallen into the black hole and cannot return. Exceeding the speed of light. As an object approaches the event horizon, it needs to move at a speed greater than the speed of light to escape the gravitational pull of the black hole. However, according to the theory of relativity, this is not feasible. Speed beyond the speed of light. As an object delves deeper into a black hole, the gravitational force becomes increasingly stronger. The object will experience an infinite gravitational pull, implying that it will be compressed and stretched infinitely, losing its original form. These characteristics make it impossible for any object, including light, to escape the gravitational pull of a black hole after crossing the event horizon. This is a crucial aspect of modern black hole theory in physics. Space exploration has provided us with crucial knowledge and deep insights into the universe. Here are some key things we have learned from space exploration missions and endeavors. Understanding of the solar system. Space exploration missions like Voyager and Pioneer have provided valuable information about the planets and objects within the solar system, enhancing our understanding of their structures and characteristics. Features of planets and the Sun. Missions such as Cassini-Huygens have expanded our knowledge of planets within the solar system, such as Saturn and its moons, as well as the characteristics of the Sun. Understanding of cosmic chemistry. Knowledge of elements and compounds in the universe has been extended through research on planets, stars, and nebulae using devices like the Hubble Space Telescope. History of the universe. Missions like Hubble and the Kepler program have helped determine and measure the distances between stars and planets, aiding in constructing the history of the universe's development. Knowledge of exoplanets. Discovering hundreds of exoplanets through missions like Kepler has opened up opportunities to search for extraterrestrial life and understand the diversity of planetary systems. Study of black holes and neutron stars. Missions like LIGO and Virgo have detected gravitational waves from events such as black hole collisions and neutron star mergers, providing crucial information about the structure and properties of these objects. Assessment of universe formation and evolution. Observing stars, nebulae, and star clusters contributes to accumulating knowledge about the formation and evolution of the universe from its earliest stages to the present. These findings not only enrich our knowledge of the universe but also contribute to a profound understanding of the nature and origin of life on Earth and within the cosmos. As of my last knowledge update in January 2022, there is still no specific and conclusive evidence regarding the existence of life elsewhere in the universe. Despite extensive research efforts to search for signs of life on other planets and exoplanets, we have not yet discovered any concrete indications of life beyond Earth. However, the search for extraterrestrial life is an active and highly intriguing field of research. Ongoing exploration missions and space telescopes such as the Kepler Space Telescope, Hubble Space Telescope, and upcoming projects like the James Webb Space Telescope are providing valuable insights into planets that may support life and searching for signs of components potentially related to life. Meanwhile, astrobiology research is exploring information about environmental conditions and chemistry that could support life, as well as how life might exist and thrive in different environments. The quest for extraterrestrial life remains one of the greatest challenges and holds the promise of revealing important insights into the diversity of the universe. We employ various methods and tools to search for signs of life in the universe. Here are some primary means. Space telescopes. Hubble Space Telescope observes the universe across different electromagnetic spectra, including both visible and non-visible light. James Webb Space Telescope, JWST, expected to open up the ability to observe exoplanets and analyze their atmospheres. Exoplanet observations. Projects like Kepler and TESS monitor changes in brightness when an exoplanet transits in front of its host star, providing information about the size, shape, and distance from the parent star. Atmospheric analysis. If we can observe the atmosphere of a planet, analyzing its composition can provide clues about the possibility of life. The presence of gases such as pollutants from living organisms could be a sign. Water detection. Since water is an essential element for life, detecting water on planets or exoplanets can be a crucial indicator. Radio signal detection. SETI, Search for Extraterrestrial Intelligence, projects are actively searching for radio signals from extraterrestrial civilizations. These could be radio, microwave, or energy signals that cannot be explained by natural sources. Presence of important chemicals. Studying chemical compounds crucial for life, such as amino acids, in cosmic environments. Energy program. Searching for traces of energy conversion processes, such as photosynthesis, can provide information about the existence of ecosystems and living entities. All these methods are being employed to research and search for signs of life in the universe, creating a comprehensive and multifaceted picture of extraterrestrial life beyond Earth. Exploring the universe faces numerous significant challenges, and here are some of the most daunting aspects. Vast distances. The distances between planets, stars, and star clusters are immense. Signals from space take a considerable amount of time to reach Earth, making exploration and communication challenging. Technological challenges. Developing technologies robust enough to explore and study the universe is a major challenge. Spacecraft propulsion systems, energy sources, and life support systems in space present significant engineering challenges. Harsh space environment. Space environments contain various elements that can be harmful to humans and equipment. Strong radiation, microgravity, and the hazards of space debris are considerations in planning exploration missions. Search for extraterrestrial life. Searching for signs of life beyond Earth requires advanced technologies and research methods. Identifying life in unfamiliar and non-standard artistic environments poses a significant challenge. Health risks for humans. Space travel poses health risks for the human body, including the effects of microgravity, space radiation, and the challenges of maintaining life in weightless conditions. Risk from asteroids and comets. Asteroids and comets pose potential hazards to spacecraft and space stations. Developing strategies to deal with these risks is a crucial research challenge. Understanding the universe. There is still much we do not know about the universe, from its formation to fundamental physical phenomena and its current state. In-depth research and understanding of the universe represent a long-term challenge. These challenges necessitate global collaboration, substantial investment in resources, and continuous innovation to overcome and make progress in the exploration of the universe. As of my last knowledge update in January 2022, there are still many mysteries in the universe that remain unsolved. Here are some of the key mysteries. Structure of the universe. We still do not fully understand the organizational structure of the universe, from the arrangement of stars and galaxies to how they interact and arrange themselves in the vastness of space. Nature of dark matter and dark energy. Dark matter and dark energy, comprising a significant portion of the universe, remain major subjects of research. Their exact nature and their impact on the structure and development of the universe are not fully understood. Cause of universal acceleration. The phenomenon of the universe's accelerating expansion is a mystery. Understanding the cause of this acceleration and whether it might change in the future is a significant task in astrophysics. Nature of black holes. While we have gained much knowledge about black holes, their exact nature, especially what happens inside the event horizon, remains a mystery. Characteristics and formation of nebulae. The properties and the formation processes of nebulae, the beautiful clouds of gas and dust, are still areas of ongoing research and insufficient understanding. Understanding the origins of life. If life exists elsewhere in the universe, we need to understand the conditions and processes through which life could originate and thrive. Properties of dark light. Dark light, which makes up a significant portion of the universe, is not fully understood. Its properties and effects on the structure and development of the universe are still areas of exploration. These mysteries continue to challenge the scientific community, requiring ongoing efforts to decode the existence and operations of the universe. There are several exciting plans and projects being planned and implemented for the future of space exploration. Here are some important and interesting plans. Artemis Program. NASA's Artemis program aims to return humans to the Moon and establish infrastructure for deeper space exploration. The goal is to bring the first woman and the next man to the Moon. Mars exploration. Both NASA and private companies like SpaceX are developing plans to send humans to Mars. SpaceX, under the Starship project, is researching the possibility of sending humans to and even living on Mars. James Webb Space Telescope, JWST. The JWST is one of the largest and most complex space telescopes ever built. It is set to be launched into space to explore the deep universe and search for signs of life on exoplanets. Nancy Grace Roman Space Telescope. NASA's Roman Space Telescope is another significant project designed to survey the universe and study up to 100 million stars within the Milky Way. Gateway Space Station. NASA and their international partners are planning to build the Gateway, an international space station in lunar orbit, as a starting point for exploration and research on the Moon. Exoplanet research. Projects like the Kepler Space Telescope and JWST focus on researching exoplanets and investigating the possibility of extraterrestrial life. Commercial exploration plans. Private companies such as SpaceX and Blue Origin are developing plans for space exploration and creating commercial opportunities in space. These plans not only represent innovation in scientific research but also open up new opportunities for international collaboration and economic development in the space sector. Exploring and understanding the universe in the coming years requires global collaboration and significant investment in resources. Here are some means and strategies we can use to expand our knowledge of the universe in the future. Space exploration missions. Continuing space exploration missions is crucial for studying planets, the Sun, and other cosmic structures. Missions like the Artemis program, lunar exploration, and Mars research play significant roles. Space telescopes. Ongoing development and deployment of space telescopes such as the James Webb Space Telescope, JWST, and future projects are vital for studying the origins of the universe, exoplanets, and deep space structures. Research on black holes and neutron stars. Advancing our understanding of the properties of black holes and neutron stars through observations and simulations can provide crucial insights into astrophysics and the formation of large structures. Dark matter and dark energy research. Intensifying research on dark matter and dark energy, both through observations and theoretical experiments, to gain a deeper understanding of their nature and effects in the universe. Studies of exoplanets. Utilizing telescopes and new technologies to study exoplanets in detail, especially those with conditions conducive to life. Industrial exploration and private ventures. Supporting private space exploration by companies like SpaceX, Blue Origin, and other enterprises to create commercial opportunities and enhance accessibility to space. Research on nuclear physics and radio signals detection. Conducting research in nuclear physics and detecting radio signals can provide new insights into the physics of the universe and unexplained natural phenomena. The advancement in these areas, coupled with global collaboration and the application of advanced technologies, will help us expand our understanding of the universe in the years to come. The formation and development of the universe is a complex and fascinating topic in the fields of astrophysics and cosmology. Here is a brief overview. Formation of the universe. First few minutes. Immediately after the Big Bang, the universe was hot and dense, expanding extremely rapidly. Within a very short time, the universe expanded at an extraordinary rate. After the first 3 minutes, as temperatures cooled, high-energy particles began to combine to form protons and neutrons, along with other particles. After 380,000 years, the temperature dropped to the point where atoms could form. The combination of electrons, protons, and neutrons created hydrogen, helium, and some other light elements. Evolution of the universe. After 100 million years. During this time, light began to move freely through space, and the universe became more transparent. After 1 billion years, large-scale structures began to form through the clustering of bright and dark regions, giving rise to large objects like star clusters and galaxies. After 13.8 billion years, present, the universe continues to expand. Stars and galaxies form, and we have systems like the solar system. Planets and other large space structures continue to form through processes such as accretion and interactions with other structures. Unanswered questions. Nature of dark matter and dark energy. About 95% of the universe is made up of dark matter and dark energy, the nature of which remains one of the biggest mysteries in astrophysics. Accelerating expansion of the universe. The phenomenon of the universe's accelerating expansion is a significant challenge, and ongoing research aims to understand its causes and future implications. Organizational structure and distribution. The way galaxies, star clusters, and other large space structures are organized and distributed is also a topic of extensive research. Understanding this process provides a deeper insight into the origin and development of the universe and is a central area of research in astrophysics and cosmology. The acceleration of the universe, known as the cosmic acceleration, is a phenomenon that modern astronomers and physicists are deeply studying. Currently referred to as the expansion of the universe, it is not only expanding but also accelerating in its expansion over time. The question of why and whether it might change in the future remains a significant challenge. Why is there cosmic acceleration? Currently, the most widely accepted explanation for cosmic acceleration is the existence of dark energy in the empty space, known as the cosmological constant or dark energy. This is a form of energy that normal empty space contains, contributing to negative pressure, creating a repulsive force pushing the universe apart. Can it change in the future? The question of whether the cosmic acceleration might change in the future is a crucial aspect that the research community is actively exploring. There are several proposals and assumptions. Pressure of dark energy. The cosmic acceleration might change if the pressure of dark energy does not maintain its current value. If it changes over time, the acceleration rate will also change. Changes in dark matter. Cosmic acceleration might be influenced by the properties of dark matter. If dark matter has new interactions or different characteristics, it could impact the rate of expansion. Different dark energies. Various models assume the existence of different forms of dark energy, and variations in them could lead to changes in the expansion rate. Ongoing research. Research on cosmic acceleration is a developing field, and our understanding may evolve with additional data and new studies. Currently, we are still in the process of researching to gain a deeper understanding of cosmic acceleration and its potential for change in the future. Measuring the distance between stars and other celestial bodies is a crucial task in astronomy and requires creativity and sophistication in measurement methods. Here are some common methods. 1. Parallax. Parallax is an observable phenomenon when we change our perspective from two different points. In astronomy, we use the change in the apparent position of a star as Earth orbits the Sun. The distance can be calculated using the parallax angle and applying trigonometric formulas. 2. Redshift and blue shift. Redshift occurs when celestial objects move away from us, increasing the wavelength of the light they emit. Blue shift, on the other hand, occurs when objects move towards us. By measuring this shift, astronomers can determine the velocity and, consequently, estimate the distance. 3. Observing Cepheids and variable stars. Certain types of stars, such as Cepheids and RR Lyrae variable stars, exhibit characteristic periodicity. By measuring the expected and observed periods, astronomers can calculate the distance. 4. Observing galaxies and star clusters. For star clusters and galaxies, the arrangement and structure can provide information about distance. The measurement of luminosity and brightness can also be used to determine distance. 5. Absolute magnitude measurement. Measuring apparent magnitude, m, and absolute magnitude, m, of an object allows the calculation of distance using the formula equals 5 log 10 mm equals 5 log 10 d, where m is the apparent magnitude, m is the absolute magnitude, and d is the distance. These methods often need to be combined and cross-verified to produce accurate and reliable. Measuring the distance between stars and other celestial bodies is a crucial task in astronomy and requires creativity and sophistication in measurement methods. Here are some common methods. 1. Parallax. Parallax is an observable phenomenon when we change our perspective from two different points. In astronomy, we use the change in the apparent position of a star as Earth orbits the Sun. The distance can be calculated using the parallax angle and applying trigonometric formulas. 2. Redshift and blue shift. Redshift occurs when celestial objects move away from us, increasing the wavelength of the light they emit. Blue shift, on the other hand, occurs when objects move towards us. By measuring this shift, astronomers can determine the velocity and, consequently, estimate the distance. 3. Observing Cepheids and variable stars. Certain types of stars, such as Cepheids and RR Lyrae variable stars, exhibit characteristic periodicity. By measuring the expected and observed periods, astronomers can calculate the distance. 4. Observing galaxies and star clusters. For star clusters and galaxies, the arrangement and structure can provide information about distance. The measurement of luminosity and brightness can also be used to determine distance. 5. Absolute magnitude measurement. Measuring apparent magnitude, m, and absolute magnitude, m, of an object allows the calculation of distance using the formula equals 5 log. Gravity is a force that acts between two objects with mass and is described by Newton's law of gravity. According to this law, every object with mass exerts a gravitational force on every other object, and the magnitude of the gravitational force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Here are some key points about the impact of gravity. 1. Newton's law of gravity. This law states that every object with mass exerts a gravitational force on every other object, and the force is proportional to the product of their masses and inversely proportional to the square of the distance between them. 2. Effect on planetary motion. Gravity between a planet and the Sun is the primary force that creates the orbit of the planet around the Sun. For objects moving in space, gravity is a crucial factor in determining their trajectories. 3. Role in cosmic formation. Gravity not only influences the motion of objects within the solar system but also plays a significant role in the formation and development of large structures such as galaxies and star clusters. 4. Ability to shape the universe. Gravity is essential in shaping the structure of the universe and has a major impact on the formation and behavior of celestial bodies. 5. Mysterious black hole phenomenon. Gravity is responsible for the mysterious phenomenon of black holes, where the gravitational force is so strong that light cannot escape, creating a region of total darkness. 6. Comprehensive influence. Gravity exists everywhere in the universe and acts between all objects with mass. This all-encompassing nature influences everything in the universe, from the motion of planets to the formation and structure of galaxies. Gravity is one of the most fundamental factors in astrophysics, and its understanding has provided valuable insights into the structure and behavior of the universe. The string theory is a theoretical physics framework that aims to unify the foundation of gravitational theory and quantum theory into a single comprehensive framework. Here is an overview of the scientific basis of string theory and its applications in cosmological research. Scientific basis of string theory. Strings as fundamental entities. String theory posits that fundamental particles are not point-like but rather tiny, one-dimensional strings. The oscillation and movement of these strings give rise to various particles and force fields. Exploring length and extra dimensions. Strings can oscillate in multiple dimensions, including length and extra dimensions, creating quarks, electrons, and other particles. This multidimensional aspect provides additional degrees of freedom in the theory. Supersymmetry. String theory incorporates the concept of supersymmetry, suggesting a symmetry between fermions and bosons. This introduces a broader range of particles and helps address certain issues in particle physics. Applications in cosmological research. Enhanced understanding of gravitational force. String theory is being used to attempt to unify Einstein's gravitational theory and quantum theory, providing a more comprehensive understanding of the gravitational force in the context of small-scale particle physics. Investigations into black holes and dark matter. The mathematical tools provided by string theory are applied to study black holes and gain insights into the nature of dark matter, helping to elucidate some of the mysteries of the universe. Exploration of extraspatial dimensions. String theory introduces the concept of extraspatial dimensions, offering new possibilities for understanding the structure of space and time. This may contribute to resolving current challenges in gravitational theory. Connection between small and large-scale physics. String theory aims to create a unified theory that describes both small-scale particle physics and gravitational physics in a single framework, bridging the gap between these two aspects of physics. While string theory is a complex and challenging field of research, it holds the promise of providing new insights and potential solutions to the mysteries of the universe. The diversity in the structure and shapes of celestial bodies in the universe is a result of various interacting factors and complex natural processes. Here are some primary reasons explaining this diversity. 1. Formation processes. Celestial bodies form through processes such as accretion, where matter and mass come together due to the gravitational force. This process leads to a diversity in size, mass, and structure of celestial bodies. 2. Ability to rotate. Celestial bodies can rotate around their axes. This rotation can create distinctive shapes and impact the surrounding environmental conditions. 3. Influence of gravity. Gravity holds celestial bodies like planets and stars in specific shapes and influences their structures. The interaction between objects and gravitational forces can create unique features. 4. Effects of gravitational force. The gravitational force can shape and mold celestial bodies, affecting their overall structure. The interaction between different objects and the gravitational force can result in diverse shapes. 5. Impact of energy and light. Energy from sources such as light and heat can influence the structure and shape of celestial bodies. This energy can lead to phenomena like explosions, illumination, or the creation of specific environments. 6. Collisions and interactions. Collisions and interactions between celestial bodies can lead to dynamism and changes in structure. Such events can alter shapes and contribute to the diversity in space. 7. Time and evolution. Time progresses, and celestial bodies undergo processes of evolution and gradual change over time. This change may involve the loss and accumulation of matter. This diversity is a result of the complex interaction between natural factors and forces in the universe, creating an incredibly rich and varied system. To measure and understand the expansion rate of the universe, scientists employ various observational methods and use remote sensing techniques. Here are some key methods and ways we can comprehend the expansion rate. 1. Quasar observations. Quasars are extremely bright and distant sources of radiation. By observing these objects, scientists can measure the redshift, a phenomenon caused by the expansion velocity shifting light towards the red end of the spectrum. The greater the redshift, the higher the expansion rate. 2. Asteroid observations. Asteroids within the solar system carry information about their origin and formation time. By studying the velocity and trajectory of asteroids, we can measure the expansion rate of the universe. 3. Observing gamma rays and high-energy events. Data from gamma rays and high-energy events, such as supernovae or other large energy sources, can also provide information about the expansion rate. 4. Measuring galaxy constants. Parameters like the Hubble constant, h, and density parameter, omega m, are used to describe the expansion rate and the structure of the universe. Experiments and measurements on galaxies and the cosmic context help determine these constants. 5. Measuring infrared redshifts. Observing regions in infrared with redshifts also provides information about the expansion rate, as light from distant sources can be stretched and redshifted. 6. Exploring distant galaxies. Space exploration missions such as the Hubble Space Telescope and instruments measuring water vapor layers on the Moon can offer crucial data about the expansion rate. By synthesizing information from these methods, we gain a better understanding of how the universe is expanding and can lead to new insights into its organization and structure. The combination of nuclear physics and astrophysics provides a comprehensive approach to understanding the origin, development, and structure of the universe. Here are some crucial aspects that this combination brings. 1. Evolution of the universe. The merger of nuclear physics and astrophysics helps us comprehend the formation and evolution of the universe from its early days. It is linked to the increase in mass, the creation of chemical elements, and the formation of celestial bodies like stars and planets. 2. Chemical element formation and fusion processes. This combination helps us gain a deeper understanding of the fusion processes in star cores, leading to the creation of various chemical elements. These elements are then dispersed throughout the universe through events like supernovae. 3. Origin and distribution of energy. It provides insights into the origin of energy in the universe. Processes like nuclear fusion and nuclear fission in stars and significant energy events like supernovae help determine how energy is generated and distributed in the universe. 4. Integration of quantum physics and gravitational theory. The combination of nuclear physics and astrophysics aids in constructing unified models for quantum theory and gravitational theory, aiming to understand phenomena at both the cosmic and subatomic scales. 5. Understanding interactions in the universe. This combination allows us to grasp the interactions among various components in the universe, from nuclear particles and light to dark matter and gamma rays. 6. Challenges in current understanding. It enhances our ability to address current challenges in theoretical physics, such as gaining a better understanding of the expansion of the universe and the balance between nuclear physics and astrophysics. This synergy plays a vital role in building a comprehensive picture of the universe and addressing fundamental questions about its origin and organization.